Make it clearer. Thank you for that very kind introduction. Let me just say that I've been at CUNY for my entire academic career, and this is the first time I've been to this particular institute, but it is always amazing to me how diverse and how interesting the many aspects of this university can be. And even though I teach at Lehman College in the Bronx and have graduate students here at the Graduate Center, it's always a pleasure to come to a new part of the university that I haven't known before, but I hope I'll get to know better in the future. Let me just say a few things about what I'm doing here, talking about the 10 classics of ancient Chinese mathematics. From the introduction, you'll have heard that my early research was devoted to the history of Western mathematics. My first book was on the German mathematician Georg Cantor, the founder of transfinite set theory. Following that, I took a slight detour thanks to the American bicentennial when I was constantly being asked to talk about some aspect here or there of American mathematics, and found that the American philosopher Charles Sanders Peirce had actually done some things that were very interesting in relation to the work I'd done earlier on transfinite set theory, in developing his own theory of the infinite and of infinitesimals to solve the problem of continuity. And if any of you have studied philosophy, you know that the problem of continuity and the problem of infinity go all the way back to Zeno and the paradoxes of motion in ancient Greece. But it wasn't long before the bicentennial was over and I was looking for a new research topic, and it was suggested by a colleague of mine at Caltech that I might be interested in writing a biography of Abraham Robinson, the mathematician who was born in Breslau, barely got out of Nazi Germany in 1933, did his undergraduate and graduate work in Jerusalem at the newly founded Hebrew University. And then in 1940, he won a fellowship from the French government. You should all be worried about fellowships. They might not come at the best possible time, because this landed him in Paris in 1940. And of course, having been born in Breslau and carrying a British passport when the Germans invaded France at the beginning of World War II, he is a Jewish mathematician, felt particularly vulnerable, and literally on foot, donkey, cart, and bicycle managed to get out of France onto a barge that took him to England, where he spent the war doing research for the Royal Aircraft industry. And he became a member of the Free French forces under de Gaulle in exile. But he went on to become a great logician and mathematical analyst, and invented something called non-standard analysis, which is a way of turning the infinite that Georg Cantor, my previous subject of interest, had turned into the inverse, namely infinitesimals, the world of the infinitely small. But it was in the middle of my work on Abraham Robinson that I got an invitation from the National Academy of Sciences in Washington. Would I be interested in going to China and spend 6 months there? The only catch was that I had to give a lecture anywhere in China I might be invited on any subject in the history of science. But all of my expenses would be paid for, either by the American Academy or the Chinese Academy. And I thought, you know, this is a golden opportunity. 6 months in China, a country that I'd not really had a chance to visit previously. I'd been to Taiwan, I'd been to Hong Kong, but not to the mainland. So I thought, well, I'll just go and see what it's about. And I was very fortunate to spend 3 of those 6 months in Beijing at the Academy for the History of Natural Sciences, the Institute for History of Natural Sciences. And there I met a wonderful group of historians of mathematics, beginning with Du Shiran, Guo Shuchun, Liu Dun. You'll be hearing a little bit more about some of them later. And I realized that there was very interesting material in ancient mathematics about which I knew virtually nothing. I came back to this country, having visited more of China than I've had a chance to see subsequently, going all the way out to Urumqi, Dunhuang, Langzhou, Xi'an, Suzhou, Shanghai, not to mention various universities in Beijing. So it was a great introduction to China. I came back and I had a great time, but I didn't really start to think seriously about research on this subject until a student from Taiwan Normal University came to the PhD program in history wanting to do a PhD in the history of mathematics. This is Huang Wansheng, who wrote his thesis on a very important Chinese mathematician of the 19th century, Li Sanlan. And at the end of his PhD, he went back to Taiwan, where he's now professor of mathematics at Shida in Taipei. But while he was here, I thought, maybe this is a voice from above saying that you should begin to take this opportunity to learn Chinese, study the history of Chinese mathematics, about which you knew a considerable amount. I did that. Then was invited back to Beijing. And with this group of mathematicians that I've been working with previously, we devised a project. And that project made it possible, under the auspices of the National Endowment for the Humanities, to bring my colleague Liu Dun here to the United States. And he was here at the Graduate Center as a visiting scholar, working for a year on a project that we devised to translate the 10 classics of ancient Chinese mathematics into English. And we decided we'd do parts, not all of it, because there's some overlaps and redundancies. We began that project some time ago. I'm still learning Chinese. We're still learning about these texts. It's really an unending project. But every year we learn more and more about these ancient texts. And this project is slowly coming to a conclusion, I'm happy to tell you. But this is basically how I got into this subject in the first place. This evening, what I'm going to do is to try and tell you a little bit about the nature of ancient Chinese mathematics, what it's like to work on this subject, the kind of work that's being done now by colleagues both East and West. I'm not going to talk about all of the 10 ancient Chinese classics. That would require at least a graduate seminar and maybe 10 more lectures, one for each of these classics. But I'll tell you at least a little bit about each one. And if you'd like me to come back on another occasion and talk about any one of them in more detail, I'd be more than happy to do so. Literally, each one of these 10 classics has an interesting life of its own. So I'm just going to really scratch the surface this evening. Well, that basically is just a little bit of context. Why have I called this lecture this evening, The 10 Classics of Ancient Chinese Mathematics, Adversarial or Authoritarian? And maybe now if we can bring the lights down a little bit, you can actually begin to see the slides a little more clearly. This is actually a title that I borrowed from my colleague Jeffrey Lloyd. And Jeffrey Lloyd's book not long ago, Adversaries and Authorities, Investigations into Ancient Greek and Chinese Science, literally takes up this question of what can we say comparatively about historical topics between ancient cultures, specifically in the case of his interests, Greece and China. And if you know something about ancient Greek science, you know that it has its origins in the pre-Socratic philosophers, beginning with Thales, Anaximander, Anaximenes, Heraclitus, Parmenides. They were great debaters. This all grew out of the Greek interest in what was the one substance that could be used to explain everything in nature. And Thales thought it was water. But then Anaximander came along and said, well, if water is the one thing from which everything proceeds, how do you account for fire? It's opposite. And thus began the Greek problem of opposites in ancient philosophy. Anaximander thought maybe the answer was air. Anaximenes thought maybe it was the boundless. Heraclitus thought it was fire as a process, but not as an actual material substance. And it's also said that in the context of the Greek democratic tradition, people learned that it was necessary to argue back and forth the logic of a particular position, particularly when you were arguing political points in the Greek political context. So Jeffrey Lloyd basically comes out in this book saying that Greek science is adversarial, and it advances through the kind of argument that goes back and forth in the sense of rhetorical debate. Chinese science, on the other hand, he saw largely as authoritarian. Once an authority, an ancient text was established as a canon, it was all right to comment on it, but it really wasn't expected that you would have an adversarial kind of advance of scientific knowledge as seemed to be the case in ancient Greece. Well, I'm going to ask whether or not this kind of a very rough characterization of Chinese mathematics versus Western mathematics as authoritarian versus adversarial is very useful. And I have to say that I've painted this in very broad terms. Jeffrey Lloyd is much too subtle an historian to see the picture in as quite as yin-yang, black and white terms as I've presented them. But for the purposes of our discussion this evening, I'm just going to let it go at that. Okay. Having said that much about the context of where we're going this evening, let me just say a little bit about the earliest record we have of mathematics in ancient China. And this dates literally back to the Zhang dynasty between the 16th and the 11th centuries before the Common Era. Prior to that, we have some evidence of rudimentary geometric designs in pottery, for example. We have various kinds of bone utensils with various geometric figures on them. And during the Zhang dynasty, improvements in agriculture fostered various kinds of divisions of labor. And we've actually got a slide for the transparency that we can switch to the transparency for a minute that gives you a sense of that. You need to... We also have various kinds of circular granaries, for example, ceremonial vessels, evidence of exchanges that led to the production of the first Chinese coins. In the 14th century, in the Shang dynasty capital at Xiaotun, near Anyang, in Henan province, a whole series of discoveries were made in terms of, and now I'm going to go back to the slide that we had previously. These Shang dynasty plastrons or turtle shells. And these were actually used for divinatory purposes, but weren't discovered until the 19th century. In other words, none of this information was known until about a century ago. And as the French historian of Chinese mathematics, Jean-Claude Martzloff, has said of the discovery of these Shang dynasty prognosticative turtle shells, discovered in 1899, an important discovery, he said, which led to a complete revision of all that was then known about ancient China. And there were thousands of these inscribed bones on turtle shells or various plastrons, the bottom side of the turtle, that were excavated. And it turns out they have, in terms of the divinatory records you see here, a way of putting these into a fire that then cracks the bone. And then a person who's knowledgeable in all of this can look at the lines and numbers the lines and actually then begins to interpret what the oracle is going to be. Now, in terms of the numbers that we find on these oracle bones, which are the earliest written evidence we have of mathematics from ancient China, they range from 1 to 30,000. With special characters for 10 or 100 or 1,000 or 10,000. This is one reason why Chinese doesn't need a 0, because there is a special character for each of the powers of 10. So if you want to talk about 20, you have 2 10s, or if you have 200, it would be 2 100s. So if there's no hundreds, it simply doesn't appear in the written record. It's a really ingenious way to write numbers without requiring the use of a 0. The largest of the numbers that we find from ancient China, however, is actually in the 9 chapters. This is a book that I'll get to in a moment. It's one of the classic of the 10 great works of ancient Chinese mathematics, and is probably the most important of them. But in the 9 chapters, in chapter 4, which is on short widths, there's a problem number 24. And it gives the volume of a sphere as being 1,644,866,000,000, and you can see the Chinese were adept at being able to write, at a very early time, very large numbers. Well, the next figure you see here shows another way in which ancient Chinese mathematics was actually a part of the construction and the development of what we would call the circle and the square, represented here by Fu Xi, with a carpenter's square, or Zhu, on the right side. You can see the square there. And then his consort is on the left, Nuwa, and she holds the compass, or Gui. And from these two instruments, as you know from Euclid, if you've studied Euclid, but from the square and the circle, you can virtually develop most of basic geometry, at least. Not conic sections, but you can at least get virtually everything else. And so this gives us another context for mathematics in ancient China. And these are actually taken from paintings that come from the walls of tombs that have been excavated in China. Another context that I'll just mention briefly that requires mathematics for its full development and description is astronomy. And here you see some of the earliest observations preserved on silk, actually, of comets. And these are the earliest depictions we have of Halley's Comet, made famous by Isaac Newton when he developed a whole theory of comets in his Principia. But out of this theory, eventually his colleague Halley developed the predictions of the return of Halley's Comet that made his name famous in association with these observations of that same comet that we have from these very early ancient Chinese records. Here you see another depiction of comets from this same record. We also find reasons for applying mathematics in the context of astronomy. And this is just one depiction taken from Christopher Cullen's very interesting book, a translation of the Zhou Suan, the earliest of the 10 mathematical classics, which is really a book on astronomy. But it contains a great deal of mathematics because, just as in ancient Greece, it was necessary, if you were going to develop an accurate astronomical model, to use mathematics in understanding it. And this is one of the Earth plates that is associated with one of these sure cosmic models in the early 2nd century BC. There's yet another context in which mathematics arises in the context of ancient China, and that's, of course, in the development of standard weights and measures. Now, when China was first unified by Qin Shi Huangdi, the first attempt to unify writing and measures and weights was undertaken. But this is actually a somewhat later standard bronze measure from the Qin dynasty that uses standard measures that we can then find being discussed in mathematical texts like the 9 chapters. And I'll get to that in just a minute. Now, we're used to talking about the commerce back and forth between East and West in terms of the Silk Route. And many of you have doubtless been on that Silk Route if you've been to China. Actually, the English concept of a Silk Route is rather a misnomer because there wasn't just one Silk Route, there were actually many. There was a northern route that went across the steppes of Russia. There was the Silk Route that we're used to thinking of, sort of midland going from Urumqi, Turfan, Dunhuan, Langzhou to Xi'an. And then there was the southern route that often went by water, by India, to the Levant, and then to the Latin West. So it's not just one Silk Route by any means. But what's interesting is that commerce wasn't just going from China to the West, bringing exotic spices and silks to the Mediterranean. But the Russians were the first to call the Silk Route from the west to the east by another name. And does anybody happen to know what it was that has become popular now as the way of referring to the route that went from the west, from ancient Rome to China? Sometimes called the glass route, because it was ancient Roman glass, something that was highly prized in the West, discovered probably in the Levant, but an extraordinary substance because of its translucent quality, regarded as a very rare commodity even in ancient Rome. But these are ancient Roman vessels actually found in Chinese contexts. And another example of the importance of commerce between East and West that I also want to mention briefly is Buddhism. Buddhism, of course, brought a lot of the interests of Indian mathematics and astronomy into China. And in fact, there's one area in which we'll find one of the texts we're going to look at this evening becomes rather controversial, insofar as it deals with very large numbers. A text that is very similar to Archimedes' text, the Sand Reckoner, in which he develops a system for describing very large numbers. Some people have suggested that this idea of writing very large numbers came into China from Buddhist sources, and we'll take a look at this possibility a little bit later. But certainly, the introduction of Buddhism was an extremely important factor in Chinese civilization, and it also plays a role in the development of Chinese interests in astronomy and mathematics. But the road also goes the other way, just as the Silk Road and the glass roads are moving back and forth, so are the mathematical roads. And a little bit later, I'll tell you something about the research of one of our colleagues in Singapore, Lam Leong and Ang Tian Se, who have written a very interesting book which argues quite persuasively, I think, that what we call the Hindu-Arabic number system actually had its origins in ancient China. But as I said, I'll get to that a little bit later. And finally, the last indication of the importance of this translation back and forth between East and West, I'll simply mention in terms of some of the extraordinary reliquaries that have been found recently, often in the foundations of temples. This, a series of gold and silver inlaid boxes with this little piece of Roman glass at the very center. And this one, also from Lintong, but the one that is most vivid in my mind is the one from Famen Su, which also has a similar set of relics. But that's actually a small piece of Roman glass that contains one of the sacred relics, or a finger of Sakyamuni. So again, the importance of this travel back and forth between East and West is an important part of our story to keep in mind. Until recently, the best known of the ancient works of Chinese mathematics were available only in a partial version that had been printed in the Southern Song dynasty. And this did not include a work that was unearthed just a few decades ago and was first reported in this edition of Wenwu in 2000, at least in terms of the complete text. Here's the first page of the text of a early mathematical work that was found on bamboo strips, almost 100 of these bamboo strips, the title of which is called the Suan Shu Shu. And the Suan Shu Shu, as you'll see here, has been variously translated as the Book of Arithmetic. I prefer to translate it as the Book of Numbers and Computations, and I'll say a little bit more about that later if you like. This is the way in which this text first appeared in the Wenwu edition. As you can see, there is a little bit of punctuation, but it doesn't tell you where the text stops at one bamboo strip and moves on to the next one. This is slightly problematic because this first section is about multiplication, and it's extremely jumbled up. It tells you to multiply 1/2 by 1/2 and 1/4 by 1/4 and 1/3 by 1/3, and then it jumps to something else and then jumps back to something else. It seems clear that the bamboo strips were actually somehow out of order. A year later, Peng Hao published another edition in which he gave the actual bamboo strips, and lo and behold, you would have thought that a simple rearrangement of these bamboo strips would give you a completely logical interpretation of this text. And I've actually got a transparency that will show you exactly what's happening with this, I think. Let's see. Yep. Actually, I've got a whole series of transparencies here, so why don't I just let you put the first one on and I'll comment them as we come along, okay? This actually just gives you a sense of the emperors in the period in which the tomb that I'm talking about, where these bamboo strips were discovered, actually come from. And the reason this is relevant is because this tomb that we're talking about contained a history, and it was the history of the second year of the reign of Lu Ho, who was a Dowager Empress regent. And so this tells us that the tomb probably comes from between about 186, 180 before the Common Era. So this was very important information for dating the tomb itself. The next transparency is actually a copy of what this second emperor, the second year of the Emperor Lu Ho looks like. The next slide, and you can see it's from a Japanese edition. The Japanese have been very interested in these materials, and in fact, while we're changing transparencies, I'll just tell you that right now there are two groups that have worked most on this early mathematical text, the Suan Shu Shu, these bamboo strips. One of them is in Japan, a group of historians of mathematics working in Osaka. The second group is working at Shida University in Taipei. And these are the two largest groups of people devoting themselves specifically to working on this early mathematical text, the Suan Shu Shu. The next transparency is a representation of what one of these tombs looks like. And you can see all sorts of artifacts are found in the tombs. Here are a bunch of individual bamboo strips. You can tell that when you pull these out and start to look at them, to reconstruct the proper order is going to be rather tricky. And the next slide gives us yet another example of what this would have looked like. We want to get up to the bottom here again. Here's another tomb, and again, here you can see a bamboo book, most likely in the lower right-hand corner. The next transparency gets us, I think, to the beginning of the heart of the mathematical matter. Okay, here's the way the Suan Shu Shu begins, the book of arithmetic. The very first section is about mutual multiplication, okay? And it begins with 1 sun times 1 sun is 1. And you can sort of read this for yourself. You get down to 1/2 sun times 1 chur is 1/20th of a square chur, and then there's a character at the bottom of this particular strip, yang. We don't know who this yang is. There's another person's name that appears on some other of these strips named Wang. Whether these were the scribes that were actually responsible for transcribing this book, whether they may have been students who had been working on that particular problem, whether it was a matter of reference, we just don't know. The next slide. Okay, tell us how the text jumps from 1/3 sun to 1/8 sun, goes on. The text then jumps again to yet another set of multiplications without any unit. The sun is now missing, we're just given multiplications. And the next slide is the last part of this text. And is there one more slide there? So you can see this is all jumbled up. And this is a reconstruction of what the text presumably should have been like if the mathematician who had done this had logically progressed from the early set of multiplications using the measures of sun and chi down to another set of multiplications, which are at the bottom of this page, I think. If you can move this to the bottom. Yeah, which produce, just go all the way down. This is a whole set that don't have any units attached to them. The only problem is that if you look at a single one of these strips, it also jumps back and forth between multiplications using units and some without. And it's very hard to explain how this could happen, unless the scribe himself had made a mistake. Or maybe the scribe didn't really know what he was transcribing. And it's my theory, and this is based in part upon discussions I've had with a number of people who know a great deal more about ancient bamboo texts than I do. But when I was at Cambridge working at Clare Hall, I was very lucky. Clare Hall, Cambridge University, has one of the great centers for the study of ancient Chinese science. It also has one of the great groups working on history of Chinese archaeology or Chinese civilization, anything related to China. Cambridge University is a wonderful place to be. The first day I arrived in Cambridge, Clare Hall, I went in and sat down for lunch. And it's communal dining there. You go and you sit down, and you sit at a table. If the table is full, you move to the next first table where there's a seat, you sit down wherever there's the next place. So I just went in, sat down, group of people already in conversation. We started talking. The person at the head of the table said, well, who are you? So I said who I was and why I was there and what I was doing. He said, oh, very interesting. I'm interested in China too. At the end of this meal, he said, let's go in and sit down. So we went and had a coffee and sat down, and he introduced himself because we hadn't really exchanged names in the middle of this whole lunch. He said, I'm Michael Lowy. Well, Michael Lowy is probably one of the most eminent people working on this kind of material. He's an expert on Han Dynasty, whatever you want to call. But certainly the archaeology, the tombs, the manuscripts, the records. He's one of the editors of the Cambridge History of Ancient China. And it was Michael Lowy who first told me, these bamboo slips come in two sizes. There's the imperial size, which is lengthy, and then there's just the everyday version, which is about half that size. And it occurred to me that this text gets broken up at exactly about halfway through one of these bamboo strips. And maybe what happened is that it was a short version of the original Suan Shu Shu that a scribe was given, got mixed up, and so just copied what was there, not really understanding the mathematics, and that's what we have at the beginning of the Suan Shu Shu. But it's still a mystery as to exactly how this beginning part of the text should be interpreted. Okay, we can now go back from the slides to the Suan Shu Shu itself. So if you can remove the postcard from, there we go. Okay, so this is this whole first section about multiplication. And as you can see, there's no indication here of where the bamboo strips begin and end, so there's no way to even begin a rational reconstruction that's very satisfactory from this version that was first published in 2001. Here is another rendering of this same section. Here's a page giving you a number of the different problems. Each one of these sets out a different problem in the Suan Shu Shu. And here's a problem that is very interesting because it's about lacquer and how you're supposed to mix lacquer in various proportions with water, or in this case, a kind of an oil maybe, or a kind of a paste, and how are you supposed to mix water and various kinds of paste together to create this kind of routure. These two characters, however, appear in this text, but they never appear in any other Chinese document, so no one knows what this is, what they are, how they should be pronounced, what they're doing in this problem. So this is another level at which these texts provide real difficulties. Characters that appear that we don't have any other contextual ways of understanding what their meaning or what their sense might be. Well, this is the Suan Shu Shu as Peng Hao published it a year later in his own book. And here you can see on the left what these bamboo rods look like. And it was some 200 of these rods that were put together, studied by scholars over the course of some 20-25 years, and eventually Peng Hao managed to publish at least a preliminary version of the text in 2000, and then this version with a commentary in 2001. This is not the first slip in the series, it's actually number 6, but if you turn this one over on its back, this one, which is the first in the set of bamboo slips that he reproduces in the cover of his book, this actually contains the name of the book itself, and it's the only place at which Suan Shu Shu actually appears. But we assume that when this was rolled up, this appeared on the outside, and whether the scribe himself wrote this, or whether it was simply written as an inventory device for identifying this roll when it was put in the tomb, is really unclear. And paleographers have been trying to figure out if there's a connection between the titles on the 7 texts that were discovered in this tomb, and they were all jumbled up, and they've all been reconstructed by various working groups. Some deal with medicine. One deals with the 2nd year of the reign of Lu Hou, which we've already seen. This is the mathematical text. You can imagine the amount of work that went into just making it possible, first of all, to get these slips into some kind of an order, and then try and create a version that is actually readable and you could then print and begin to work from. Here are the 3 characters. The character that appears on the bamboo slip is a very ancient version of Suan, but virtually every printed version of this text uses a more recent version. Certainly not the simplified version, but still the Suan of the 2nd character here. And here's the first problem that I'm going to say something about, but not until I've had a chance to give you at least a sense of what some of the other problems in this text are like. So just one second. Okay, well, in the interest of time, since I'm getting close to my 45 minutes and I've only gotten into the first quarter of what I was going to say this evening, I'll just tell you that among the problems in the Suan Shu Shu that are of interest are some that deal with the exchanges of grains, which are very interesting problems. Others deal with the computation of various volumes of tombs or of circular granaries. But one of the most interesting is a pair of problems. This is the first of the problems, problem 61, which talks about from a circle cut a square. And it just begins at the top, E-U-N psi fun. And then it comes to the end and it says ling qi er yi si, and then you'll realize it just sort of stops here. And it's not clear exactly how this problem should end, or exactly how it should be understood as it turns out. This is my translation. And I'm not going to go into the detail now. You can ask me back another time if you like, because just this one problem here, four-way. Up here it's this si-way. What is this way here? What should that refer to? This is just one of the problems that is controversial for reasons that we'll see in a moment. The first group that began to work on the Suan Shu Shu in the Chinese context, the first translation actually was produced in Japanese by Joichi Shigeru. And this is the first Chinese edition or collation or printing of the text with a commentary following the version in Wenwu that we just saw. But the Wenwu was just the text with no commentary in 2000. So this comes out by a team of students of Huang Wansheng, my former student from here at City University, all of whom got together and individually were given parts of the text, and then they got together and discussed each one, and very quickly put out this collation of the text. And here's their collation at the beginning of the text. Here's that first problem, how they unravel the sequence of multiplications that we talked about earlier. Here's this problem, 61 and 62. From a circle, cut a square, and the next one is, what would you guess? From a square, cut a circle. Or maybe that's what it means. Anyway, this is their understanding of the problem. That the first problem, 61, begins with the circumference of a circle, and then from that you're to find the length of the inscribed square, the side of it. And the converse to this problem, they say, is given a square, the side of the square, find the diagonal or the circumference of the inscribed circle. There are a lot of problems with this reading of the text. I won't go into them all right now. One of the problems is that they see these two problems as numerically inverse. And in fact, if you look at the numbers in the text, they are numerically inverse. But they can't be geometrically inverse because one is a square inscribed in a circle and the other is a circle inscribed in a square. So if the numbers are truly inverse, this can't be the right interpretation of the problem geometrically. And I'll just leave it at that for now. The second person to produce a collation of these two problems in the Suan Shu Shu is Guo Shirong at Inner Mongolia Normal University, Shu Yibao's former alma mater. And he has spent a lot of time and has discussed this in detail with his mentor and probably one of the greatest authorities on ancient Chinese mathematics, Li Di, who is the professor and founder of the institute there in history of science and mathematics at Inner Mongolia Normal University. Anyway, this is the first page of his collation of the text. And this is how Guo Shirong looks at problem. He's only numbered the problems in which he's interested. So his numbering is not the same as the Tongshun groups. This is his collation of the text. He's had to change some of the numbers to make his understanding of the text work. But you remember that controversial word way that I pointed out earlier? What does this way mean? Way might mean circumference, but he takes way to be the difference between the diagonal of the circle and this difference between the inscribed square and the, if you had the inscribed circle here and its diagonal, this is the difference that he says is the proper interpretation of way. For problem 62, he inverses this and says the way now is the difference between the diagonal of the square and the diameter of the inscribed circle. A very different interpretation requiring very different numbers for the problem. which he has no problem in just changing the numbers to fit basically this interpretation. The next person to collate the Suan Shu Shu is our colleague at the Institute for History of Mathematics in Beijing, or the History of Natural Sciences in Beijing, but he's an historian of mathematics and probably the world's leading authority on Liu Hui, Guo Shuchun. And Guo Shuchun, in his interpretation of this problem, here's the first page of his collation of the text, and here's his collation of the problem. He basically agrees with the interpretation that's given by Guo Shirong. There are some minor differences in terms of the numbers, but I won't go into those. This is Peng Hao's version of the Suan Shu Shu, his collated edition with commentaries now. Here's the title page of his collation. And here's his interpretation of problem 61. And problem 62 is here. And this is the interesting one because he understands this to mean a problem of given the square, find the area of the inscribed circle. So he sees this as an area problem, not one of circumferences or perimeters. The problem is the fact that the numbers in these two problems are truly inverse, but the statement of the problems are not. So there is a disconnect between the problem as it's set and the text and the solutions as they're given. This is my translation of the first of these two problems. This is my translation of the second. And this is my solution. And I've written a lengthy paper about this, and if you are interested, let me know. I'll be happy to send you a copy. I won't go into the details now, but if you interpret psi as not to cut from a circle a square, as if it were a circular piece of wood, and then just cut a square out of it, so the square is going to be smaller than the circle. But if it means inscribe or incise, so given a circle, inscribe and circumscribe a square, you can use the numbers that are given in the text to make the actual coordination of the problem and its solution fit with one minor problem that I won't go into now. And here's my solution to the second part of the problem involving the square and circles, inscribing circles inside and outside to the square. Okay, that's problem 6162. There are three other problems that I just want to mention very briefly about the Suan Shu Shu because they're what I call multitasking problems. And it may have been that these were problems that a professor of mathematics or a teacher might well have set students. Now just read through this problem. The first time I read through this problem, I said to myself, what in the world can this possibly be about? It says, carrying charcoal from a mountain. In one day it's possible to carry 7 dough of charcoal to a wagon. The next day 1 dan can be gathered charcoal can be taken to the wagon, is transported to a government post. Now, if you wish to go to the government post carrying charcoal from the mountain and transporting charcoal the long distance to the government post, the question is how much charcoal is delivered in 1 day? Well, this problem made no sense to me the first time I read it. The various collations by Guo Shirong, Guo Shuchun, and the Tongchun group really are not terribly helpful.
That's the way elementary algebra students see their word problems.
Well,
It doesn't make any sense to them either.
We'll see how one way that this may have been a didactic text is to go into this next problem, 47, lutong, or bamboo utensils. And it says that in 1 day you can either cut down 60 stalks of bamboo, or you can make 15 lutong. There are 15 of these maybe bamboo ladles. No one's quite sure what lutong is, but let's just say it's a bamboo ladle. If one person is told to both cut down bamboo and make ladles, and you also know that you can make 3 ladles from every 1 bamboo you cut down, how many lutong can you make in 1 day? And the method says take 60 as the divisor and take 50 times 5 times 15 as the dividend, and you get the answer. And virtually every commentator on this problem says that it's wrong. And they give various ways of reinterpreting to make it right. Okay? I'll just tell you that when I first read this problem, I went through it, and I said, okay, you cut down a bamboo stalk, you make 3 lutong. Okay, you take 1 bamboo stalk, that's 1/60th a day. 3 lutong, you can make 15 of those in a day, so that's 3/15ths of the day plus 1/60th. I went through the problem that way and discovered that this was right. The answer is correct. So now, why are my colleagues saying that it's wrong? And does this have anything to do with that charcoal problem about which I didn't know anything in terms of how to solve it? Well, the solution came with a third problem in this series, which is about feathering arrows. And the norm says one person in one day can make 30 arrows or feather 20 arrows. Now, if you want to do both in one day, both make arrows and feather them, how many can you make altogether? And the answer is 12. And the solution to this is realizing that if you can make 30 arrows in one day, it takes 1/30th of a day to make an arrow, and then it takes 1/20th of a day to feather it. So add 1/30th and 1/20th, and how many of those are there in a day? 12. That's your answer. You can apply that method and go back to the Lutong problem. It doesn't quite work. And the reason it doesn't quite work is because if you use this method, you're going to get the wrong answer, because there's a dependency here between the fact that you've got one bamboo strip, but you can make 3 Lutong from that one bamboo strip. If you take that into consideration, then you can solve the problem. The first problem about carrying charcoal is understandable, but it still doesn't make practical sense. If in one day you can take a certain amount of charcoal to the cart, or in one day you can take the total amount of the cart to the government, what happens if you want to do both? If you understand it this way, you get the answer the text gives. So you apply the method, you get the right answer, but it doesn't make the problem very practical. Okay, but these are very interesting problems, I think, from a very early Chinese text. Now, that is the earliest Chinese text that we have in terms of the actual text, because it's on bamboo strips, and these bamboo strips actually survive. We can hold them, we have them. All of the other classical texts come from editions that are as late as the Southern Sung printing or after that. So they're really quite late, even though this is dated to around 100 BC to 100 AD. The text of the Zhou Bi Suan Jing has been very nicely translated by Christopher Cullen. Here's the first page of the Zhou Bi Suan Jing. And this is basically, as I've said, an astronomical text. It deals with various theories of the heavens and how you can measure the height of the sun, for example. And it does that by using gnomons and shadows, so it includes a very nice elementary sort of trigonometry. Here are 2 of the diagrams of the Zhou Bi Suan Jing. This must resonate if you've just seen those 2 problems of the Suan Shu Shu about inscribing circles in squares and squares in circles. I won't say anything more about this now. But here is a very interesting diagram from the Zhou Bi Suan Jing. And it relates to the Pythagorean theorem. And here you can see the right triangle, right? And here's 3 units on one side, 4 units on one side, 5 units on this side, and the square here on the right and the square on the top are equal to the square on the hypotenuse. And this was later interpreted and commented on by Liu Hui in his 9 chapters. Here's another diagram that no one's quite sure what it's doing or how it really plays a role in the Zhou Bi Suan Jing. And here's yet another one that doesn't really quite fit into the scenario of that book, but the first diagram does. Here is the work that I've been talking about just by allusion until now. This many consider to be the Euclid of ancient Chinese mathematics, the Zhang Suan Shu, the 9 chapters on the art of mathematics is how it's usually translated, although not always. And here you see the title page from the Southern Sung printing. Unfortunately, we only have 5, or is it 6 books in the Southern Sung printing. And it's not a complete text, so it's been reconstituted from later versions and printings and things like the Yongle Dadian and other sources. Before I say anything more about what's in it, let me just tell you about one of the most basic techniques of ancient Chinese mathematics that give it a character very different from ancient Greek mathematics. And it's something called the in-out complementary method. Now, if you're in a student classroom and you ask your students, how would you be able to prove that given this rectangle, and if you know these 2 lines intersect and are perpendicular to each other, how do you know that area A is equal to area B? Under what circumstances is that true, and how could you prove it? Well, you might think for a while. And here's the solution, the out-in complementary method. Another way to look at it is, when is the red triangle equal in area to the blue triangle? Well, the answer is when the point of intersection lies on the diagonal. All right, you say, well, okay, fine, but now how do we prove this? One of the things that's often said about ancient Chinese mathematics is it didn't have a concept of proof. Well, I'm about to show you that it does, and it's really not only a transparently simple idea, but it turns out to have penetratingly deep consequences. And this is the out-in complementary method. Okay, now that we know that we can prove this if the intersection point lies on the diagonal, take a look at the rectangle. Now, we all know from basic Euclidean geometry that if you take the diagonal of the rectangle, you would all agree that it divides the rectangle into two equal parts, right? So we've got the red triangle on the top, the blue triangle on the bottom, and those are both equal. The Chinese didn't say it as explicitly as Euclid did in his axioms of geometry, that equals added to equals are equal, or that equals subtracted from equals are equal, but it's just a logically obvious proposition. If someone in China had written this down, we'd have a Chinese Euclid before Euclid. But that's the effect of this in-out principle. Because we know that here's a smaller triangle on the bottom, and these two triangles are equal. And the same is true of the upper rectangle. The diagonal gives us two equals, which we then subtract again. And the result is that we've taken these two equals out, these two equals out. The two triangles were equal before. What's left must be equal. Voila. A very nice proof by the out-in complementary method. A and B are equal if that point lies in the diagonal. I leave it as an exercise to you to prove that if it's not on the diagonal, you don't get the result. Okay? It's left as a exercise for the student.
Are there colors in these texts?
They mention colors. We don't have the diagrams, but they do explicitly refer to colors. The diagrams have been reconstructed later, and they follow the colors that are referred to in the text. And we'll see that in just a minute.
So there are words in lieu of the colors?
Yeah, it says blue or green or red. Yeah, it says, we'll see. Yeah, we'll see in just a minute how Liu Hui does this with words that refer to colors. Okay, now, I'm going to apply this to a very simple geometric theorem using this out-in complementary method. How do we prove that the area of a triangle is equal to 1/2 the base times the height? How do we prove that? Can we prove that the area of this red triangle is equal to 1/2 the product of the base and the height? Well, using the out-in method, maybe you can see where I'm going here. If this we consider the in part, and this is the out part, take the out part, and we're going to move it into the in part, and voila, we have the proof that the area of the triangle is equal to the base times 1/2 the height, or 1/2 BH, or however you want to express it. But again, very transparent. Any student in a geometric classroom, I think, can see intuitively how easily this kind of proof works. And it's a proof that comes up again and again in ancient Chinese mathematics. Okay? You can just visually see the equality at work here using the in-out complementary method. Okay, now let's go back to perhaps the greatest of all theorems from, well, at least the first book of Euclid's geometry, namely the Pythagorean theorem, or as I prefer to call it, the Gogu theorem. This is a theorem that states, and Liu Hui says directly, and let me see if I have the quotation here. Yes. Why don't we put this on the transparency so everybody can see exactly how the language looks. Oops. Okay, so this is what the Chinese says in English translation. The Go square is the red square, the Zhufang. The Gu square is the blue square, the Qingfang. Putting pieces inside and outside according to their type will complement each other. Then the rest of the pieces do not move. Composing the Xian square, taking the square root will be Xian, the hypotenuse. Okay, say to yourself, what is all this? Things moving around according to their type and one thing or another. What is this really about? Well, let's go back, now that you've seen the language and the reference to colors, and see exactly what he's saying. All right. We're now thinking about the in-out complementary method, right? So here you can all see this is the Pythagorean right triangle. Here's the Go square, the red square that Liu Hui talked about. Here's the Qing square, the blue square that Liu Hui talks about. This is the square on the hypotenuse, okay? Let's talk about the overlap of the blue and the green square as the inside. And let's say everything out of the hypotenuse square is on the outside, okay? If we think of it that way, here's the outside, okay? Here's the inside. And now you can all see what's going to happen. How would you move the red pieces to the inside? Well, here's how you move the red pieces to the inside, okay? Move this piece up here, move this piece from down here, and you can see these are going to fit very nicely in, which they do, except for this one spot here. But now we've got to move the blue parts that are outside onto the inside, and you can see where that's going to go. This comes down here very nicely, and this little piece comes right over here, and voila. We've got the out moving in, and a very nice visual proof of the Pythagorean, or the, go-goo theorem, right? The go and the goo come together, moving the outside parts to the inside, to give us a proof of the Pythagorean theorem. And the important thing to remember, I think, here is that this isn't just a proof about a triangle that is 3 units, 4 units, and 5 units. This holds in general for any right triangle. It just happens to be stated here, maybe because the diagram comes from the Zhou Suan Jing. The Zhou Suan Jing isn't interested in making this mathematical point the way Liu Hui is when he writes his commentary on this section of the text. Okay. Well, this has led some people, like Frank Swetz and T.I. Kao in their very popular book about the 9 chapters. They've only translated here book 9, which is the one that is devoted to right triangles and the go-goo theorem. It's interesting that there are no problems about triangles in the Suan Shu Shu. Something seems to have happened between the writing of the Suan Shu Shu, which is probably Warring States or pre-Qin at least, and the writing of Liu Hui's commentary on the 9 chapters to have made right triangles so important. They appear in the Zhou Suan Jing. Maybe that's why they didn't appear in an arithmetic text like the Suan Shu Shu. But was Pythagoras Chinese? An interesting question. Well, we might as well ask, were the Egyptians Chinese? Because we know that the Egyptians, using ropes, and you can see these are rope stretchers, they went out and literally mapped the geometry of the Earth. Geometry is Earth measurement, and they used these ropes because they knew that a configuration of 3 knots, 4 knots, and 5 knots, if they're even, will give you a right angle. The agrimensoren of ancient Rome used the same method. If we go to ancient, well, read in the Bible, the rope stretchers lay out the land. If we go into the Indian mathematical classics, we also find rope stretchers who use these ropes to get basic 3, 4, 5 regular, what we would call Pythagorean integer-sided triangular trios. And then we come to ancient China, and what do we find is the word that means diagonal. It's xian. And what does the word xian mean? Can anybody tell us? What does xian mean? It's often translated as lute string or thread. But again, it's the idea of something stretched across. So it's very interesting that the concept of a stretched rope or a string, the word hypotenuse in Greek means that which is stretched across. It comes from the Greek word tenusa, that which is stretched. So this concept of rope stretching is obviously a very important part of the origins of these mathematics. So to suggest that Pythagoras was Chinese or that Chinese was somehow Pythagorean, Liu Hui may have been, is problematic because the same experience seems to have guided the mathematical intuition in all of these cultures. Well, here's one of the most well-known problems in the 9th book of the 9 chapters. It gives you a reed in a pool, and it gives you the dimensions of the pool and how tall the reed is. And if you pull the reed right over to the edge, it just comes, how tall must the reed be? You can solve this very easily using the go-goo principle. It turns up in ancient Indian mathematics. So does this next problem about a piece of bamboo. You know how tall the break is and how far away it is from the bottom. How tall is the whole piece of bamboo? Again, a problem that turns up in Indian and Western mathematical literature. Here's the Zhang Suan Shu and the commentary on the segment of the circle that is discussed in Liu Hui's commentary. Now remember, this Southern Song text printed in 1213, until we found these bamboo strips with the Arithmetic Classic, was the earliest text that we had, an actual hand source. It goes back, we know, to the Han period. But even so, we don't have any of those Han texts for the zhang Suan Shu or the zhou Suan Jing. They both come from this Southern Song printing. Well, here's the diagram. Any of you who have studied the problem of finding the area of a circle or the circumference of the circle in the Greek tradition have seen this kind of a diagram. It's how Archimedes solves the problem as well. Archimedes is a little more sophisticated. He uses inscribed and circumscribed regular polygons to give us a limit in both directions. But Liu Hui understands exactly what's at stake here, and he tells us that you can go as far as you like, and eventually you reach a point where you don't need to go any further. Your approximation is good enough, is what he eventually says. Well, this is an interesting addition to the 9 chapters. It's the Sea Island Mathematical Manual, the Haidao Suan Jing, which Liu Hui originally wrote as a 10th chapter to the 9 chapters. He said, you know, after studying the 9 chapters all my life, writing this commentary, there's something very important missing. There's a whole set of problems that aren't discussed in the 9 chapters. So I'm going to add them in a treatise of its own that develops a method that I call the double difference method. And this double difference method is basically the way in which you can identify or measure the height of a distant mountain. It's at sea. You can't cross the sea. You can't measure it directly. But you can measure it indirectly by looking at the shadows or the sightings that are cast. Now, this is the method that was used in the zhou Suan Jing to measure the height of the sun. If you assume that the sun is casting a shadow on a flat earth, and you erect 2 gnomons that are of the same height, and then you look at the difference between the length of the shadows and the difference, let's see, the double difference is the difference between the 2 gnomons and then the difference between their 2 shadows. You can then triangulate the height of the island. This is the idea behind the double difference method. And Liu Hui devotes all of what was to be the chapter 10 of the 9 chapters, but it eventually, because it was so important, became a separate classic text of its own. And here you can see the diagram where the double difference aspect comes into play to determine the height of the sun in the zhou, or here the height of an island in the Haidao Suan Jing. Okay, since I've more than used up the time that I was told I was allotted, I'll simply say that my favorite of the chapters in the 9 chapters is actually number 8. This is the Fang Cheng chapter, and it is a way of dealing with what we would call simultaneous equations. Here we're told there are 3 bundles of top quality grain, 2 bundles of medium quality grain, 1 bundle of low quality grain. The amount in total is 39 dou. Then we've got a next set of similar combinations. And then at the end we're asked, how much of grain do we have in each bundle of the 3 types of grain? And here's the answer. To understand how Chinese mathematicians solved this problem, and it was very elegant, first of all in its detail, but secondly in its generality, it was all done with counting rods on a counting table. And these rods were put down to represent numbers, and then you would simply multiply. If you had 5 and you want to subtract 2, you'd put down 5, you'd put down 2, and then you'd take the 2 away and you'd wind up with 3. So it was an ingenious method that was basically a set of algorithms. And it meant that algorithms could be very complicated, but you just did them mechanically, and if you did them correctly, you could solve very complex problems. So,
is that the same as Gaussian elimination?
You're going to see that in just a second, because here is the matrix that we've got set up for the problem, and you can begin to see how in the various stages the manipulations are described in the Fang Cheng method. You want to isolate eventually using the triangulation method the first variable. You've got 36 of 99, so we know that the first bundle of low quality grain is going to be 99/36. They're 2 3/4 dou, okay? Then we go on and we do the same elimination for the second or the middle quality of grain. But what's interesting about this method is not just that it's a brilliant way to solve these kinds of problems using a technique that wasn't discovered in the West until centuries later. But here's problem 3. I'm not going to read through the problem, but it's basically the same kind of a problem. But look what happens. When you set up the matrix and you want to begin to diagonalize it, you need negative numbers. And so the Chinese very early, very naturally introduced the concept of negative number with no difficulty. Here's a problem where even the statement of the problem requires negative numbers, because you're selling 2 cows and 5 goats to buy 13 pigs, and you've got 1,000 surplus in cash. And when you translate this into the context of the matrix, again, a natural way to develop the concept of a negative number. And here's my favorite problem in a way, simply because it's so complicated. Here's what the matrix to solve it looks like. But again, with the algorithms in mind, you know exactly how to proceed. You simply manipulate the counting rods on your counting board. You follow the procedures. You isolate each one of these, and the answer follows very nicely. It looks complicated, but if you know the method, then you simply apply it. Here's what the text says. Method. Solve by the array rule, calculate by the sign rule. Well, Liu Hui calls upon himself to explain what this means. And this is one of the problems of these texts. They're often very laconic. They just say something like this. Without a teacher to explain it to you, you wouldn't know how to proceed. But here Liu Hui comments and tells us, some clumsy students of exact science use this rule mechanically or arrange a lot of counting rods on a carpet. You can imagine he's got this previous problem in mind, a very complex problem. They're meticulous but vulnerable without thinking it irrational to behave so, but rather saying the more the better. So to make it as complex as possible, they just go through rote by rote, but there may be shortcuts to the problem. And then here's a famous paragraph from Liu Hui. The skillful butcher always leaves plenty of room for the play of his knife through the muscles and the dissecting of an ox, so that the blade remains sharp. And what he's saying is that the smart mathematician knows what to look for. Don't just jump in and start to solve a problem doing it mechanically. There may be a better way to solve it. There may be a better approach to the solution that will make your life easier. Well, I wish I had time to talk about this text because it's truly my favorite of all the 9 classics. It's a text this is the, well, I'll maybe show you just briefly on a few transparencies why. Okay. We've already seen that part. Okay, do you want to put that on? This is how my colleague Jean-Claude Marcelov describes this text as laconique et sibyllin, laconic and virtually impenetrable to understand in his description of the Shu Shu Ji. Here's how it's been translated. I mean, the problem with this text begins with the title. You can see the various ways in which it's been translated, and no one can even agree upon the title of this text. The reason it's of interest is because, like the section in the 9 chapters devoted to Archimedes, this too develops a method similar to the one that Archimedes develops in the sand reckoner for writing very large numbers. And it's an ingenious method that makes it possible, literally, to take an arbitrarily large number and write it down in a very concise fashion. Another reason that this is a very interesting text is because it contains a word which may mean infinitesimal for a very small unit of time, shana, but this may come from a Buddhist text, and the Buddhist text was introduced into China much later than is possible for this text to have been written by the author to which it's ascribed. And so some people claim that it's actually a forgery that was written probably in the 5th century, maybe in the 6th century, not by Shu Yue, to whom it's attributed. And if you want to put this back on the... Got it? Shu Yue's name appears here. That's actually the seal of the Beijing University Library where this particular manuscript is now kept. But some people say that it may probably be a forgery by Zhang Lan. And I think his chop is on here someplace. But in any case, it's an interesting text because of the way in which it writes these very large numbers. And okay, here's how Archimedes approached this problem. You can just put each of those on, and I'll say something just very quickly about each one. This is Archimedes' treatment of the problem. There are some King Gelen who think that the number of the sand is infinite in multitude. And I mean by the sand not only that which exists about Syracuse and the rest of Sicily, but also that which is found in every region, whether inhabited or uninhabited. Again, there are some who, without regarding it as infinite, yet think that no number has been named which is great enough to exceed its multitude. Well, the next transparency is going to tell you that Archimedes says this is wrong. That in fact, I can write down the number of all the possible grains of sand. I can see that these things, King Gelen, will appear incredible to the great majority of people who have not studied mathematics, but that to those who are conversant therewith and have given thought to the questions of the distances and sizes of the earth and the sun and the moon and the whole universe, the proof will carry conviction. So he begins by saying, let's assume the earth is X size and diameter. He says, just to make this interesting, let's multiply that by 100. And he says, let's assume that a grain of sand is about the size of a piece of rice. But let's make it interesting. Make that 1/100th smaller. I can still write down the number of grains of sand that would fill that universe. And he does. And if you put the next slide on, here's basically the way in which he goes about it. He talks about the sphere. He talks about the various ways we can write numbers. And is there one more transparency there? That's the last one? Okay, then if you go down to the very bottom, it'll say, okay, that here's the way in which he works out his system of very large numbers. But what's interesting is that it's very similar to the one that we find in the Shu Shu GE. Okay, let's get back to the wind-up of what I want to say here. Okay. We've been through all of this. Oh, maybe no, I'm not. Okay, here's the Shu Shu GE. And the fact that I find this a very interesting text, but I'm not going to say anything more about it. I'm going to conclude with what, if any of you are interested in following up on the remarks I've made this evening with your own reading on the history of Chinese mathematics, here are some of the things that I think you might want to take a look at. One is a very interesting paper that Lisa Raffles published not long ago in the newsletter for the Center for Cross-Cultural Studies at Hong Kong, City University of Hong Kong. I think it's so nice that we've got a city university here in New York, and we've got a very nice city university in Hong Kong that has the same kind of mission in a way that we do, and there's a very interesting Center for Cross-Cultural Studies there. And she writes in this article that there is a problem in talking about triangles in Chinese mathematics when there is no word for triangle in Chinese, at least not in ancient Chinese. How do you then conceptualize triangles? I won't say more about that now, but just think about that as a conceptual problem. If we're dealing with mathematics and we know it involves triangles, but the Chinese never thought it was necessary to come up with a word for triangles. There's also the interesting connection between religion and the day-to-day life of the Chinese experience, and here's the Temple of Heaven, how it builds in the architecture of squares and circls. And here is Xu Jie, the last mathematician I'm going to mention just briefly, in his Si Yuan Yu Jian, the precious mirror of the four elements. Because in this text, this is what was said of Zhu Shijie and his importance, that with two other ancient mathematicians, he was said to form a tripod. And the reason he's so interesting goes back to what I told you just a little while ago about Chapter 8, the Fan Cheng chapter in the 9 chapters on the method of arrays and matrices to solve simultaneous equations, because what he did was to devise a matrix method using the various positions on the counting board where you would put your counting rods down to allow you to represent the coefficient positions for various combinations and various powers of as many as 4 unknowns at any given time. And this just shows you how you would represent x plus y plus z plus u with this idea on the counting board. Here's how this particular equation would be set up. And using this, he gives 4 paradigmatic examples that then suffice for solving the problems that go through the entire book. Again, this is something that I'm grateful to my colleague Shu Yibao for having spent a number of weeks, actually. We went through each of these problems literally line by line to try and figure out how they were done. Because the statement of the problems here are really too laconic to really explain the full working of the precious mirror. But let me tell you, it's a very impressive level of mathematical accomplishment that Zhu Shijie reaches in this particular document. Here's the second problem if you're interested in what it asks you to do. Okay, I promise I'm coming to an end now, and that is to recommend one of the earliest of the great surveys of ancient Chinese mathematics. Actually, it covers everything down to the 19th century, and the work of Li Sanlan. That is Li Yan and his protege, Du Shuren, Chinese Mathematics, A Concise History, that was translated not long ago in 1987 by Crossley and Lun. It's a very nice basic introduction to Chinese mathematics, perhaps more sophisticated in terms of its historiographic interests and in terms of the wider context of Chinese culture, in which Jean-Claude Martzloff puts his history, is his study of Chinese mathematics. And then a very interesting article that was written by Chris Cullen when the American Mathematical Society had its meeting in Beijing in 2002. And he talks about the didactic character of Leo Hui's commentary and how useful the approach that Leo Hui takes to solving this Pythagorean theorem or Go-Gu problem actually can be. You can see this is a different color configuration based upon what we find in the diagram in the Zhou Suan Jing. And here's the book that I mentioned earlier by Lam Le-Yong and Ang Tian-Se, which argues that if we look at the way in which square roots are actually derived, or how multiplication or long division are carried out in the Western Arabic Hindu tradition, the startling thing is not that the numbers are Arabic and the references may be Hindu, but that the methods are actually Chinese and go back to the Sun Suan Jing. And they argue that if we take a careful look at this, it's possible to suggest that in fact our decimal place valued Hindu-Arabic numeral system should actually be called the Chinese Hindu-Arabic system, because the whole idea goes back to the concepts that are present as early as the work of the Sun Suan Jing. Here's the Sun Suan Jing, the text that literally explains how you do long division, how you do square roots, how you do cube roots on the counting board. And all the methods are spelled out in this text. I won't say anything about the importance of the discoveries that have been made at Dunhuang. These are after the Song edition. What was discovered at Dunhuang were the earliest extant physical remains of mathematics that we've had until the discovery of the Suan Shu Shu. If there were time, I'd talk about commerandas with ancient Greek and Roman mathematics. Here's the oldest surviving diagram for how you actually extract a square root, and you can see what you do is you start with a square. You take the largest square that you can get up to that square, and then you look at the factors 2a or 2b and b squared. If this becomes the b, and you subtract that, and it gives you a nice algorithm for finding, to a very high degree, as high as you like, however far you wish to go, square roots. Well, this brings me back to a very brief conclusion based upon Jeffrey Lloyd's book, Adversaries and Authorities. To what extent can we say ancient Chinese mathematics was authoritarian? Well, I think it's true that a book like the 9 chapters established itself as a classic text, and very early on, all we find after that are commentaries. But those commentaries are not so beholding to the original text, that they're not willing to criticize it and add their own very important emendations. And of course, the first to do that was Liu Hui himself. But Liu Hui, for example, in trying to solve the problem of the volume of a sphere, realizes that he doesn't have the methods to do it. And so he says, you know, I'm not going to try and fool you. I'm not going to tell you that this is the last word. I'm sure that later a mathematician will come along who will finally solve this problem, and eventually, some years later, that was the case. So I think while there is an authoritarian aspect to ancient Chinese mathematics, just as there is to ancient Greek science, I think there's also an adversarial component. Mathematicians knew when they had a better method, when they could extend it further, and that's exactly what Zhu Shijie did. And extending those methods from chapter 8 in the 9 chapters, the matrix methods for linear equations basically, into equations that would handle 4 unknowns to as high a power as you might like. Well, this is just yin and yang on the cover of the adversarial authoritative juxtaposition in Jeffrey Lloyd's book. And here's the follow-up to Jeffrey Lloyd's book that you may also want to take a look at. It's by Jeffrey Lloyd and Nathan Sivan. Nathan Sivan is probably one of the most eminent historians of Chinese science, certainly in this country, or writing in English. They engage themselves in a dialogue. Sivan, the authority on Chinese science, Lloyd, the authority on Greek science, and try to really tease out the differences and the connections, the similarities between the two. I'm sorry to say, it only has 2 pages devoted to mathematics. But for the larger question about comparing Chinese and Greek science, it's a very interesting book. Well, and finally, these are the proceedings of a meeting that was held at Bellagio, the Rockefeller University's research center and study center in Bellagio, Italy, a few years ago, about the transmission of mathematics across cultures. And it begins with a very interesting article by Kurt Vogel, one of the great German historians of mathematics, talking about a problem that begins in the Chinese ancient tradition and finds its way from India into the Islamic, Arabic mathematical context, into the Latin West. Clearly an indication of how important mathematics moved from China to Western mathematical knowledge. And so basically, that concludes my talk. I'm sorry that it's at least twice as long as you asked for. But in any case, I commend you for having been able to sit as long as you have. And I'm happy to answer questions as you may have them. Yeah. I'm sorry, the lights are kind of bright, so you know it's sort of like when you hear about actors on a stage, they can't see the audience. It's kind of hard for me to see. So, but yes.
In the equations, simultaneous equations, where the equations are actually not linear, 4 variables, is there any similarity between that method and the Chroma basis method?
You know, when you mentioned, oh, isn't that Gaussian elimination? I always worry about trying to say, because it looks similar to us, to say, well, you know, there may be a connection. Now, there's obviously, on the psychological level of how you work these problems out, a sense that we're trying to diagonalize a matrix. But they're working with counting rods on a board, and it's a very physical and mechanical kind of a thing. It's also not quite as general as we might like it to be, because it's limited by the four quadrants of the board, and certain parts of the board have to be set up to be interpolated to give you various combinations that don't occur there logically. So in some respects you can say yes, but I think there are important things to keep in mind that they're not really exactly the same thing. But I think it's maybe typical of mathematics that you get 2 mathematicians in a room and give them an idea. They may come up with the same way to go about solving it, or they may come up with very different ways of solving it. The best example I can give of that is one that our colleague at Hong Kong University, Xiaoman Kung, gave not long ago. He was running one of the mathematical Olympiads. And he said, you know, it was very interesting because it was in Hong Kong. He was involved in setting up the questions and reading the papers. And he said there were 3 teams that came in first, second, and third. The Americans, the Chinese, and the Russians. He said they were almost identical in terms of how well they did it. But what was amazing, the Americans, there are five people on each of the teams, and they're given a set of problems. They do the problems, and then they're graded on how they went about them. He said, you know, we looked at how the Russian teams went about doing a given problem. They all approached it in this way, or the Chinese, they all approached it this way. When it came to the Americans, there was a problem, and 5 kids, and each one did it a different way. They each had a different approach to it. And I think, well, they were the first. I mean, they came out first in the Olympiad. And I think if there's anything that my colleagues in China want to learn from the West, and why they like to come here to study, or why they like to have us go there to teach, is to somehow give them this sense that there are different ways to approach a problem. There isn't just one way, and I think that's what Liu Hui meant by saying you've got to be open to the fact that there's not just one way to do a problem. And if you always approach it in the same way, you're going to run into difficulties sometime. When I was in the 8th grade, I can remember in my algebra class, I loved to do everything using decimals. And my greatest rival in this class was a girl who did everything using fractions. And the person who was teaching this class was very savvy. And he knew that if he put problems on the test that could only be done with decimals, I'd do just fine, but she would have trouble. Or if they were all fractions, I wouldn't have much luck, but she'd do very well. What he eventually discovered was the best way to make sure that I didn't do everything using decimals and she didn't do everything using fractions was to put problems together that were easy to solve if you use decimals, almost impossible with fractions, and vice versa. So this is an important thing to learn, that there's no one way to go about many of these problems. And what I think is really nice about looking at these early approaches to the in-out method is that it's a very different way to looking at how to prove things that are very familiar to us, but we don't necessarily approach it that way. But once students see the transparency of the out-in method, it really can take you very far. And Liu Hui, in his discussion in the Haidao Suan Jing, these very complex problems using the double difference method, they've been interpreted by most Western mathematics using the kind of algebra and trigonometry that we're used to. And then Wu Wenjun a few years ago said, wait a minute, this is not how Liu Hui was thinking. If he used any method at all to solve these problems, he would have used the in-out method. And what would it look like then? And he then reinterpreted in the in-out method, and it was much more transparent, I think, and made a lot of sense. So it's something that is a lesson I think can still be used teaching in the classroom today. Yeah.
I remember when I was in 10th grade in geometry, you learned the hypothesis and theorems and proofs and so on. Mm-hmm. And a lot of students in the class, including myself, is involved in that in the beginning. But I'm like, I think it was last year, this lady or that lady came here the same conference.
Right.
On Chinese language and teaching try to, well, anyway, in China, how are they teaching the geometry?
Oh, you've got experts here that can tell you about that. Let Professor Han say something about that, because it's something she knows very well that I would be embarrassed to try and answer that question, frankly.
How do they teach geometry?
Yes. Do they follow the American way that I learned when I was in 10th grade, or do they use that in and out method, which is much more mechanical and
Yes.
And are we doing that, teaching the same thing in the cities and high schools?
If you have an enlightened teacher that's interested in history, maybe.
Yeah.
And the interesting thing for me as a historian of mathematics over the last 10, 15 years is go to the annual meeting of the American Mathematical Society and the Mathematical Association of America. And 15, 20 years ago, you'd have a special set of sessions on the history of mathematics. There would be, 50, 100 people there, but now 200, 300 people will come to these sessions. And they include everything from ancient Chinese mathematics to, 20th century Chinese mathematics, as well as Arabic and Babylonian. And I mean, it's just very ecumenical. And people have found that in teaching, this is, particularly in a city like New York, extremely valuable because it brings students from various cultures into the subject because, well, gee, you know, I'm from Iran, and this was how Al-Khwarizmi was doing it. You know, that's a very nice way to bring it to people that don't otherwise have a connection to the mathematics. So teachers that are motivated and are interested to use the history can. But it's tricky and it's difficult. You've got to spend a lot of time to study the history, and if you don't know the languages and you need to learn the languages, it's another level of difficulty. And what would really be nice, if any of you are still young and gifted linguistically, to learn Chinese and Sanskrit and Arabic and Greek and Latin, then you could put all this together. You remember I showed you a slide about this meeting in Bellagio. The reason we put that meeting together was we wanted to be able to talk about how did mathematics go across all these cultures. But not one of us knew all these languages. But we had people that knew Chinese and Sanskrit, and people who knew Sanskrit and Arabic, and so it was sort of like one of these, you know, chain letters where sort of we're all talking together at once, but trying to get a continuous picture. But it's a lot of work if you want to become seriously involved in this, because you need to know the languages. Yeah.
2 questions. In the 9 chapters, when they talk about the Gogu theorem, or how do you pronounce that? Gogu theorem. Do irrationals come up at all?
Very interesting question. Did the concept of an irrational number ever come up in ancient China? Depends upon who you ask. It's a fairly controversial topic because about a decade ago, a Chinese historian of mathematics suggested that there's a word that comes up in this context called mian, which is side. This side is really a substitute for the concept of irrational number, and that this argues for the existence of irrational numbers in Chinese mathematics. My own concept is, to have a concept of the irrational, you have to have a concept of what a rational number is. And one of the reasons the Western discovery of irrational numbers came up was because the Pythagoreans began with the pronouncement that everything in the world could be expressed as ratios of integers. Everything could be expressed as a over b. Okay, so what's the ratio between the diagonal and the side of a square? Assume it's a over b and you get the contradiction, and so you know there are no rational numbers that will express this. Well, this was a disaster to the Pythagoreans. Amazing to mathematicians, and it led to the Eudoxian theory of proportions to try and solve this problem, because you've got the diagonal of the square in geometry, but you have no way to represent it in arithmetic. So your arithmetic is incomplete. And this was a discussion that went on and captivated. I mean, Plato was amazed that you could discover and prove that something didn't exist. There was never any discussion like that in China, and it seems to me that if Chinese mathematics had really discovered the concept of irrational number, there would have been some discussion of that. But in fact, these mians are simply treated like everything else. If the Chinese did discover the irrational, then they assumed that they could be treated and handled exactly like the rational numbers, and there was no big deal about it. I'm skeptical. I don't think that the concept of irrationality appeared in the ancient Chinese context. But another person you should ask to talk about this is Shui Bao, because Professor Shu has devoted his dissertation to problems of the infinite in Chinese mathematics, and this question comes up there. And he's also looked very carefully at what happened when Euclid was translated into Chinese. How did they understand Book 5 or Book 10? Well, they couldn't understand Book 10 until fairly late because it wasn't translated until the 19th century. What did they make of Book 5 when it was translated? I shouldn't answer that question. You can invite him to come and tell you that story, but it's a very interesting one. So my advisor. It's just a little pro bono advertising, but needless to say. But another, I think unbiased observer was Professor Lee. So he's also read the thesis, and I think it certainly is not only a very interesting one, but